In the previous video looking at the kinetic theory of gases, we were able to explain pressure and how it arrives from the motion of the particles. In this video we're going to take it a step further and look at how temperature can be explained in terms of the motion of the particles. And so we need to go back to that equation that we finished with from the last video. So that's from the kinetic theory of gases. So basically this one is just going to be a bit of a derivation, so linking these equations and showing how we can then come up with an explanation for temperature in terms of molecule or molecular motion. So we start off with that equation, P equals 1/3 n m over v multiplied by the square of the average speed. So that should be u av squared. The first step that we're going to do here is just sort of simplify this a little. We're going to change it to PV, and hopefully that'll be a fairly obvious step, and you can understand why PV is going to be used here. So the idea behind that is that we know from the, or if we then combine that with the equation of state for an ideal gas. So just a reminder there, the equation of state being PV equals nRT. So we've got that left-hand term PV being the same, so we can equate the right-hand sides. So in that case, we can then say that nRT is going to be equal to 1/3 of nm multiplied by u, the average square of the average speed. So there's the first simplification. We're going to take it another step from there, and we'll take the capital N over the other side. So we've now got n over n multiplied by RT is equal to 1/3 m u squared. But keep in mind, if you go back to the video on moles, we looked at the fact that n is equal to the number of particles over Avogadro's number. So n equals capital N over Na, so we can rearrange that and write an expression for n, lowercase n over capital N, so we could write that as being 1 over Na. So we can now substitute in for here and simplify that expression, and instead write this as RT over Na is equal to 1/3 m u av squared. So the idea behind that is that we're sort of just trying to manipulate this into a form that we can sort of do something else with. And this next step's a little bit forced, but hopefully you'll make sense of it. This might look sort of familiar. It kind of looks close to being like kinetic energy, half mv squared. And we're actually going to kind of force that in there. So we're going to make that half m u av squared, but we can't just change 1/3 to 1/2. We need to manipulate it. So in order to do that, we'd have to multiply by 3 up over the other side. So that's going to be 3RT over Na. But to get this half factor in, we then need to actually divide. So that's going to be 3 on 2 multiplied by RT on Na is equal to half m uAV squared. And as I said, this here, this term on the right hand side now, is the average kinetic energy of all of the molecules. So, like I say, that last step a little bit forced, but introduces this idea of the average kinetic energy of the gas molecules. And so we can then simplify this one last step and rewrite it in a different way. Instead of writing half mu, we can now say that that's the average kinetic energy. So Ek with a bar on top, so that indicates that it's the average. So that's going to be equal to 3/2 of RT on Na. So there's the first part of the equation. The values for R and N here, though, they're constants themselves, so we're going to manipulate that just one last step, and we'll write it as 3/2 of a new constant. We're going to call that one K with a subscript B. I'll explain what that is in a second, multiplied by T. So you can see here this equation is in the data booklet. I think they've actually got those last two around the other way, so these two are, I think, are swapped. Ultimately, it doesn't really matter. It's just I've written them in a different order. But the idea behind this is that we've now got, as we said to begin with, a molecular interpretation for temperature. So EK is the average kinetic energy of the particles, of the molecules. And so if we know something about how fast they're moving, what the amount of internal energy of the gas is, we can then relate that to the temperature. So that would be measured in joules. The value of R is the ideal gas constant. So that value, it is a constant, so you can look up what the value is in the data booklet. Na is Avogadro's number. T is the temperature. Again, Avogadro's number is a constant, so you can look that up in the data booklet. T is the temperature of the gas in Kelvin. And the last value there in that equation that we need to know, Kb, is known as Boltzmann's constant. And it's basically just a combination of the values for R and Na. So Boltzmann's constant Kb is just equal to R over Na, and that has a value of 1.38 by 10 to the negative 23 joules per Kelvin. It is another constant though, so you can look that one up in the data booklet as well. But there we can see that if we know what the temperature of a substance is, we can figure out the average kinetic energy of its molecules, or in vice versa, the average kinetic energy of the molecules of a gas. We can then calculate what the temperature of that gas is. Like I said, both of those equations are listed in the data booklet. It's just simplifying R over Na to give you the using Boltzmann's constant instead.